Welcome everyone to chapter 2.1, the building blocks of molecules. So this chapter is basically looking at the chemistry of living things. All right, chemistry is the study of matter and the interactions of matter. And matter is anything that takes up space and has mass. And last I checked, all life forms, all living things, take up space and they have mass, which means that if we're going to understand how life works, life science, that's what this class is, we need to have at least a fundamental understanding of chemical properties and such in order to understand how life works. So what I have up here on the right is a familiar molecule to you, H2O, water. It's unusual among molecules in that it actually occurs as a solid, liquid, and a gas here on Earth in natural temperatures. Molecules can occur in these three states, plus there's a fourth one that we're not going to talk about. But generally speaking, molecules do not exist in all three states of matter here on Earth. Our temperatures just aren't extreme enough. But water does. And there's a lecture later that's just on water because life needs water. So it's pretty important to understand how it works. Water is not an element, but water is built from two different elements, hydrogen, right, and oxygen. These are two out of the 92 elements that occur in nature. So what is an element? An element is a substance that you can't break down further by any chemical means. And so if you have a water molecule, you can still break it apart into oxygen and hydrogen atoms, because that's what each of these letters represents, one atom of those elements. But once you get down to a hydrogen or oxygen element, chemically, you can't go down any farther and still retain the properties of that element. So there's 92 naturally occurring elements, but as you'll see, some of them occur in life a lot more than others, and many of them don't occur in living things at all. So let's go ahead and look at some of the elements that occur in life, right? All of these elements occur in you and in other living things. There are more than this that occur in you. There's just over 20 that do. These are some of the most prevalent elements in you. Elements are generally represented by their elemental symbol, which I've got listed to the right here of these. Many of them are pretty easy to remember because it's just the first letter of the element, like we see with carbon, hydrogen, oxygen, and nitrogen. Speaking of those four, these four compose more than, near, or just a little bit more than, 96% of your body weight. So when it comes to the chemical composition of living things, including yourself, those are the big four in terms of elements. And of course, water is H2O, so a good chunk of those hydrogen and oxygen atoms occur in water, which occur in you and in your cells. Two other elements that are also prevalent are phosphorus and sulfur. And some people focus on these six making up the bulk of your body weight rather than just these four. So phosphorus and sulfur are also relatively prevalent in living things. We've also got some examples of some metals that you need. Potassium, sodium, and calcium are all metals. Sodium and potassium are two elements where the elemental symbol is different from the first letter of the word. So potassium is a K, and I believe it's because the Latin term for potassium starts with a K, and then sodium is an A. In an elemental symbol, if there's two letters, the second letter is always lowercase. And so these pictures just show some examples of molecules built from these elements. And so sugar, this is a cube of sugar. Sugar, and there are different types of sugar, but the most common form that you'll hear about is glucose. So this is a type of sugar. And if you look at the chemical formula for that, C6H12O6, carbon, hydrogen, oxygen. 3 of those 4, right? And so we're going to run into those particular elements a lot. Also, just another example of elements in living things. Skunks obviously smell bad if they spray you. And so part of what, or I should say the bulk of what makes the smell so terrible is that it has sulfur within the spray. And sulfur has a very bad smell to it. And so that is, skunks actually make relatively good pets, I've heard, if you remove the scent glands. I think that's pretty important detail to have in there. So, what determines the properties of a particular element? Elements are built from what are called subatomic particles. The word sub means below, like a submarine, right? So subatomic means below the atom or smaller than the atom. So an atom is built from subatomic particles. And the general layout of an atom is like this. This is not drawn to scale. The nucleus is actually a lot tinier in comparison to where the electrons are, but this shows the gist of what I want you to know. So this is an atom of carbon, and if you know the properties of carbon, you will know that carbon has 6 protons and usually 6 neutrons. And so here they are, and it doesn't quite show all of them in here, but there's 6 protons and 6 neutrons within the nucleus or the center of the atom of carbon. Surrounding the atom, you have electrons, and they have that negative charge, as you can see there. Carbon typically has 6 of those as well. And we'll talk more about proton and electron number in just a second. But again, protons and neutrons are in the nucleus. The electrons surround it and exist in these things called orbitals around that nucleus. Protons have a positive charge, electrons negative, neutrons are neutral. Here's the important thing to note. I think I have the periodic table, not on the next slide. Here we go. So on this table, you're going to notice that each element has a number that goes with it. That number is called the atomic number, and it is the same always, no matter what, for every element. And what I mean is, if an atom has 6 protons, it has an atomic number of 6. Let me write that up here. The atomic number is the number of protons. Should have said that. So the number of protons determines, technically speaking, what element a particular atom is. So if an atom has 6 protons, which means it has an atomic number of 6, it's carbon. No ifs, ands, or buts about it. Even if the number of neutrons is different, even if the number of electrons is different, if protons equal 6, it is carbon. If it has 7 protons, it's nitrogen. 8 protons, it's oxygen, so on and so forth. we'll come back to this periodic table here. Wrong way. There we go. Okay, so let's stick with carbon. And by the way, just a fun thing up here, diamond and graphite are both pure carbon. Like there is nothing else, it's just carbon atoms together. But the carbon atoms arrange themselves differently, which gives very different properties to diamond and to graphite that we see in pencils. There we go. So, atomic number for carbon is 6. We defined atomic number as the number of protons. Often you'll see elements written this way, with the elemental symbol here, and then the atomic number right here, and then above it, you've got what's called the atomic mass. So, atomic number is just the protons. That never changes. If it's not 6, it's not carbon. Atomic mass, though, is protons and neutrons. And the number of protons is always going to be 6, but typically neutrons is also 6, right? So usually you'll get 12, but sometimes there'll be 7 or 8, and you can get an atomic mass of 14. If you've heard of carbon dating, carbon occurs in this format, this atomic mass of 14, called carbon 14, and it decays differently than the run-of-the-mill carbon, and they can measure the decay, and since the decay occurs at a consistent rate, they can see how old something is by seeing how much carbon 14 has decayed. So that's an example of something with variable atomic masses, but the atomic number is always going to be 6 for carbon. I mentioned the periodic table. What it is a nice way of representing all of the elements. They're listed in order of atomic number. So let's go ahead and look here. And it goes from left to right, starting at the top left with an atomic number of 1 up here, which is hydrogen. And then you've got helium with 2, lithium, beryllium, and so on down the line. And it just keeps increasing in atomic number as you go along. The familiar ones that you really want to be aware of are these 5 here. Actually, these 5 here, and then hydrogen up here. Those are the ones that you want to be aware of, where they are on this periodic table, especially 1, 2, 3, 4, especially those 4. The periodic table is arranged such that members of vertical rows actually share features in common. For example, this row right here with helium, neon, argon, krypton, xenon, and radon, those are called the noble gases, right? And that means that they're stable by themselves. So if you look at water, for example, water has 2 hydrogens and an oxygen. This is a bond between them, and that bond exists because they want to be stable, and forming that kind of bond helps make them stable. We'll get to that in a second, a little bit more. Neon, for instance, 1 atom of neon, it's already stable. It doesn't need any other element, any other atom to make it stable. It's already there. All of these are. In fact, that's why we use helium in balloons, because they used to use hydrogen. Then you had the Hindenburg disaster in Germany. I want to say World War I. But anyway, it was a hydrogen gas and a massive explosion, because this is very reactive. Helium is nice and stable. It doesn't want to form any bonds. It's not going to do anything dangerous. And Neon isn't either, because they're all noble gases in that row. In contrast to that, everything here and everything here is off by 1. Off by 1. And so they're very reactive because they're close to being in this row, but they're 1 row away. And so they're very reactive because they're trying to get that stability that those noble gases have. There's 92 elements, 25 have been observed in humans. And again, of those, only 4 of them, which I erased, but had them up here, only 4 of them make up 96% of your body mass: oxygen, carbon, hydrogen, nitrogen. Other elements that you need include phosphorus, sulfur, calcium, potassium, magnesium, zinc, etc. And I just had a picture up here of sweet potatoes because I like them and they're a good source of potassium, one of the elements that you need. Dairy products are generally a good source of calcium, another element that you need. All right, let's see here. I already kind of talked about this, but just to reiterate, these are the 2 varieties that, well, there's 3, but these are 2 out of the 3 varieties of carbon. Typical carbon, radioactive carbon-14. These are what's called isotopes of carbon. And again, note that the atomic number is identical, always is. But isotopes are when you have the same element with similar atomic numbers but different atomic masses, right? Different mass numbers here. And so they can respond and react differently, even though they're both carbon, because they are differing in the number of neutrons. And again, carbon-14 can be used to date organisms that have decayed because it decays at a specific rate. Okay. Everything we've talked about so far has been protons and neutrons. But the truth is, the nucleus of an atom, where those things live, the nucleus doesn't actually do any interacting with other atoms. So the protons and neutrons in this water, for instance, they're actually not involved in the bond that makes the water. The subatomic particle that actually does stuff with others is the electron. So electrons are the subatomic particle that's actually involved in forming bonds, and thus, technically speaking, the number of electrons determines how an atom will interact with other atoms. Because you see, here's the thing. There's a stable number of electrons that you can have if you are an atom. And that's what you want to get to. You want a stable number of electrons. And if we go back to the periodic table, all of these guys here, the noble gases, they've got it. They've got the stable number. Everybody else, they want to find a way to get a stable number of electrons. How do you do that? Well, you can get rid of some, you can take some in, or you can share. A lot of different opportunities to get to that stable electron number. So to start off with, an atom is going to have the same number of electrons as it does protons. So for carbon, which we've talked about a lot, carbon has 6 electrons because its atomic number was 6. I'm going to go sneak on back to the periodic table. Carbon's got 6. If you look up there, nitrogen's got 7. Oxygen has 8. And hydrogen, way up at the top left, has 1. None of them are stable by themselves. They're not noble gases. I'm just going to make sure that my phone is still recording. It is. Excellent. I got a new phone a couple weeks ago, so I think the video recording quality is quite a bit better on this one, which just makes me happy. Okay. Let's try and go through what's going on in this slide. So how it works is you've got the nucleus here in the center. That's where the protons and the neutrons are going to be. And then you've got, surrounding the nucleus, these things called orbitals. This is the home of electrons. The first orbital, in order to be stable, has to have 2. I've just put 2 electrons here in the first orbital of our hypothetical atom, and it is stable. If you go back to the table, I've just drawn an atom of helium, which has an atomic number of 2. 2 in the first orbital, we're stable, we're good. After that first one, after that first orbital, all of the ones that follow it are going to need 8 to be stable. So, what I've just drawn right now, stable. If you look at the periodic table, this is an atom of neon, an atomic number of 10. Stable. So, getting these orbitals stable, either with 2 or with 8, that's what atoms want to do. All right? So let's take a look at the picture up there. Hydrogen. It has 1 electron. Just 1. Just the 1. That first orbital only needs 2 to be stable, which means hydrogen atoms just need 1 more electron, and then they're good to go. Oxygen has an atomic number of 8, which means 2 in the first orbital and 6 in the second one, giving us a total of 8. Which means, to be stable, oxygen needs 2 more. So, 2 hydrogen atoms, 1 oxygen atom. This is a good place where sharing electrons is going to work. So if you look, hydrogen comes in, shares its electron with the oxygen. Oxygen gets its electron, hydrogen gets 1 of the electrons from oxygen. Hydrogen is now stable. It's got 2. The other hydrogen does the same thing. It shares 1 with oxygen, it is now stable. And if you count all of the oxygen atoms on this outer shell, all of the oxygen electrons on this outer shell, 8 electrons. Stable, 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 voila, water molecule. And in this case, they got there by sharing, as you can see in the picture. hydrogen only has that one orbital. The outermost orbital that a particular atom has is called the valence orbital, and the electrons within it are called the valence electrons. So the valence electrons are the electrons in the outermost orbital. For oxygen, it's this second one. Hydrogen, it's still just that first one. And ultimately, those are the ones that interact, the valence electrons. And again, in order to get stable, an atom's got to fill the valence orbital. And that's why they interact. That's why atoms interact the way that they do. It's all about becoming stable with the electrons in that last orbital. I'm not sure why this line of text came up last, but that's okay. So, one thing you're going to know, orbital and electron shell, those are interchangeable terms. They mean the exact same thing. All right? And again, the first orbital or shell can hold 2 electrons. Subsequent, which means the ones after it, can hold 8 electrons. Because most orbitals are going to hold 8, it's called the octet rule, because octo means 8. And again, 2 for the first, 8 for everything after. Water is formed by chemical bonds. Chemical bond is a lasting attraction between atoms that enables the formation of chemical compounds and molecules. The one that we just looked at with water is a covalent bond. Covalent is sharing, and as you saw, hydrogen and oxygen had electrons that applied to the valence orbital for both atoms. Right? So if you look back, this electron counts towards hydrogen's outer shell, and it counts towards oxygen. It's being shared. So chemical bond is lasting attraction, covalent is sharing. In living things, such as yourself, covalent bonding is the norm and is by far the most abundant bond that we see. So, simply put, covalent bonds build life. This is the one we're going to focus on the most. This is the one that is most important for this class. Ionic bonds are another type of bond. This occurs not with sharing, but with donating and receiving. So one atom will get rid of an electron, another one will receive one. And I can't remember, do I have a special slide on ionic? I do, okay, so I'm going to wait on it. Hydrogen bonds will be the last one we'll look at. This is easier to talk about once we get to the technical part of it, which we'll get to here in a bit. These pictures show a couple things. Potatoes, I love potatoes. Built by covalent bonds. Starch is built from a bunch of glucose molecules. Covalent bonds keep them together. But the salt, for instance, let's say you go to McDonald's and get their fries. I love their fries. That would be potatoes held together by covalent bonds, but all of that delicious salt that they throw on it, that would be an example of something that is ionically bonded. Table salt, sodium chloride, built from ionic bonds. Let's talk about covalent bonds then. So living things build almost entirely from these. This is when atoms share electrons, and each atom ultimately gets that stable number in its valence shell due to the sharing. Atoms of carbon, oxygen, nitrogen, and hydrogen, the big four, this is pretty much all they do. They don't donate and receive electrons, they share. Up there on the board I have salmon, which looks incredibly tasty right now. So salmon is high in protein, right? And I'm going to put something up here that you do not have to know, at least not yet, but I want you just to kind of get a visual of how this works. So this is the frame, the building block of a protein. It's called an amino acid, and you'll notice down here I put a question mark. That's because this section differs between the 20 different types of amino acids, but these guys linked together in a big chain, that's what makes up protein. So when you eat salmon like that, you're eating a massive chain built from enormous quantities of these, one after the other after the other. Carbon, nitrogen, hydrogen, oxygen, all four of them are in an amino acid. Sometimes there's a few more different ones down here, but yeah, and all of these, by the way, these lines, those are the bonds. That line says, hey, this and this are sharing an electron pair. Here they're sharing two pairs. That's where there's two lines. And so this is all covalent bonding going on in that amino acid. Okay, sometimes sharing is not equal. So take a look at water up there. Oxygen with two hydrogens. They're sharing electrons, but the electrons tend to hang out near oxygen more closely than they hang out near hydrogen. Because of that, the oxygen tends to get this negative charge to it. Right? The name for when this happens is a polar covalent bond. And think poles like positive and negative poles. So polar covalent bond is when you've got electrons hanging out more in one area of a molecule than another. In this case, they like the oxygen. So they tend to go there and make oxygen kind of negative. Since the electrons are not equally shared, it creates a polar bond, and the molecule that's involved in this is called a polar molecule. Water is a great example of a polar molecule. Another example would be sugar. Now, if any of you have ever fed hummingbirds, you've mixed sugar with water, and eventually the sugar seems to disappear before your eyes. It becomes a mixture. The reason why that happens is because sugar is just like water in that it has some negative and some positive regions on it, which causes attraction to the water, and hence it dissolves when you mix them. On the other hand, you probably have noticed that vegetable oil and water do not mix. That's because vegetable oil is a nonpolar molecule, which means it doesn't have positive and negative regions. Remember this idea of opposites attract? So, if you've got a molecule with a negative part and a positive part on a different molecule, there's going to be an attraction there. And then This would happen with sugar. You swirl it around. Ultimately, the bonds get broken and you have the dissolving of the sugar. Oil doesn't have positive or negative regions. It simply doesn't have them, which means it doesn't do the same thing with water. It doesn't have the attraction, it doesn't break apart, it doesn't mix. And if you put oil with water, you're going to get that separation like you see here. So oils and fats are two of the most common non-polar molecules, and neither one of them are going to mix with water because of that. All of this, by the way, this is all referring to covalent bonds, things that occur when you share. Okay? All of this involves electron sharing. Ionic bonding, in contrast, involves electron donating and receiving. Sometimes you don't want to share. Sometimes you just want to get rid of electron. For example, sodium, 11 electrons. It's got one more than it needs. If it can get rid of this electron, this outer shell won't exist anymore, and now the valence shell will be this one, and it has 8. Perfect. Chlorine has 17 electrons, which means it has 7 on its outer valence shell, needs 1 more. What a beautiful situation. Sodium donates its electron to chlorine. Now sodium is stable. Now chlorine is stable. So, the actual bond between sodium and chlorine occurs because of the following. Take a look at sodium. Sodium has 11 protons and normally 11 electrons. But it just got rid of one. It just got rid of one. So now it has 10 electrons. It has one more positive than negative particle, which means it's Na plus 1. And we usually get rid of the 1 and assume that a single plus means plus 1. And so it's a positively charged atom, and that's called an ion, which I think will show up here as maybe the next click. Let's see. Yeah, it's an ion because it has a charge to it. In this case, it has a positive charge, so it's called a cation, which you can see there. Chlorine, 17 protons. Remember, if it doesn't have that proton number, it's not that element. So it has to have 17 to be chlorine. 17 protons, 17 electrons, but it just gained an electron to become stable, so it's got one more negative particle than positive, Cl negative 1. And again, we just assume the 1 is there, so Cl negative. Now we've got a positive and a negative. There's your attraction. There's your bond. Right there. Salt dissolves in water, by the way, because positive and negative charges interact with the water molecule being polar, which we just talked about. So let me draw it up here. You've got oxygen, negatively charged, hydrogen's positively charged, and then you've got sodium and chlorine. The negatively charged chlorine is attracted to the positive hydrogens, and then the reverse is true for sodium. And then if you take that and you stir salt in water, you'll have it dissolve just like the sugar did. even though in this case it's a different reason why it dissolves because it's ionic bonding and not covalent. But that should do it for this unit. All right.